Okay, welcome everybody. I think we don't have to look too far around our industry to know that we're on an inevitable trajectory in a move to solid state lighting as part of our toolbox. And that's going to have a profound change on many things we do in the lighting world. By now, some of you guys may have seen Tom Littrell's Layers of Light presentation. How many have actually seen that? Okay. So you know that Tom has talked about protecting the quality of light and designing with both tungsten and solid state sources. And we think at ETC that's a very important approach to the transition to solid state lighting. I would like to take a slightly different tack today and talk about the implications in the support system for solid state lighting, what it means to the material that goes in the walls of a building or as part of power and data distribution in our systems to support solid state lighting. So I'd first like to talk to you guys about power and how we control it, because that's a key element in the move to solid state lighting. Many people have said, why do we even need to control power to LED fixtures? Why do we need to have a complex system design? Because LED fixtures simply plug in the wall like toasters or microwave ovens, and we can control them over a data link and just turn them on, right? They don't require any system design or intervention to get a system that works properly. And we think actually nothing could be further from the truth. There are a lot of very hidden gotchas in LED system design, and to think of them as items that plug in the wall and don't need any consideration as to how the system is configured or built is just simply wrong. We think there are actually two likely approaches in facilities to solid state lighting. The first, in smaller venues with less demanding designers, is that the move to solid state lighting will happen pretty much all at once. Conversion to an all LED system is likely in these smaller venues. However, in the rest of the world, where we have thousands of theaters with tens of thousands of channels of existing power distribution and control, we think the weight of that existing infrastructure in the field and the cost of moving to LED lighting is going to have a slowdown effect, if you will, on that instant change to LED fixtures. So how do we add LED fixtures to existing systems in a rational way? we think that one of the most important things in this transition is that we give the end user of a facility, the end user, not the system designer, not the manufacturer, not the building engineer, but the end user, a thing that I like to call the transition valve, which is a metaphorical thing which lets the end user move between tungsten lighting, conventional systems, and solid state lighting at a rate that they pick. Not at a rate that's picked by an engineer or a consultant sitting in an office somewhere, but by an end user in the theater who is doing shows every day. If you ask an end user who's faced with LED transition in their theater, how many LED fixtures are you going to use? How and where are you going to put them? What are you going to use them for? The likely answer is going to be, gee, I don't know. I might be using, I have a limited budget, so I might be buying one kind of fixture this year, another kind next year, and I might not know where they're going to be used or in what function. So that suggests a different kind of infrastructure for allowing a transition dictated by the end user. And now we have to come back to that whole question of why do we need to do things differently to feed power and data to LED fixtures? Well, first of all, as I said before, some people think we can leave LED fixtures on all the time and just plug them in like toasters. Well, we actually can't do that for a couple of reasons, or we shouldn't do it for a couple of reasons. The first is what I like to call a vampire power. An LED fixture with a switch mode power supply in it consumes power all the time, whether or not the console is directing the fixture to be on or not. So a fixture might consume ½ a watt, 2 watts, 5 watts of power just sitting there. So right away, if we just leave that fixture on all the time, it blows the green argument for lower power consumption. Because while we use a fixture in the theater on a very short duty cycle, perhaps 3 hours a day or less, 24 hours, 7 days a week of a fixture consuming ½ a watt, or 5 watts rapidly adds up and makes it a power hog. So right away we can say we got to turn those fixtures on and off. There's another important reason we have to turn them on and off, and that is the life of the fixture. Let's just take the complexity of a typical tungsten fixture. What does it have? It has some wire, a socket, and a light bulb. That's it for complexity. An LED fixture, on the other hand, has many hundreds more parts and a much lower mean time between failure than a standard tungsten fixture. There's lots of stuff to break in an LED fixture beyond the LEDs themselves. And that's why the story that is being told by the LED manufacturers of LED lifetime, that is, how long does it take to get to 70% of the lumen output of an LED? Typical number might be 50,000 hours. So the inevitable conclusion is, well, that means my fixture will last 50,000 hours before having a problem. And that's completely not the story. There are much higher failure rate parts in an LED fixture, like power supplies, line filters, all kinds of other stuff beyond the LED emitters themselves. So it's important for us to turn them off when we're not using them, because A, they cost a lot of money compared to a tungsten fixture. They're still an order of magnitude higher in cost, and they're inherently less reliable. So how do we make them more reliable? We use them less. We turn them off when we're not needing to use them. So ETC's developed a couple of good tools for this changeover from LED to from tungsten to LED in existing facilities, one of which is the through power module for the sensor dimming system. We have many hundreds of thousands of sensor dimmers installed all around the world, and the through power module allows the sensor system to instantly be suitable for dimming tungsten loads, switching LED loads, or both, as switched from the console. So that means when the first show of the season needs to dim a certain load at a circuit, it can do, the through power module can allow that. When it now turns into a solid state lighting LED fixture and needs to be switched on and off, it can do that. Also, the through power module offers a really unique feature, which is air gap switching, which means an actual relay in the module that disconnects the circuit from the load when it's turned off. And you say, well, why is that important? Well, certain LED fixtures, like ETC LED fixtures, will work well on electronic switching. For instance, a dimmer set at full, no problem for an LED fixture made by ETC. But there are many more LED fixtures out there from other manufacturers that don't react well to that kind of approach. They require switching off the power definitively in order not to damage the switching power supply in the fixture. So then people say, wow, this switching idea you mentioned, what a great idea, but I have another approach that would really be good. Why don't we just switch the whole theater off all at once with one main contactor? Because I can get a main contactor for a fraction of the cost of hundreds of switches on all the individual branch circuits. We'll just turn it off at the end of the day and turn it on when we come in. What about that? Well, we have a little problem there in that LED fixtures have a characteristic known as inrush current, which is much like the current drawn, the high current drawn by a cold tungsten bulb, but many more orders of magnitude than that cold tungsten filament. So what that means is when we turn an LED fixture's power supply on, instantaneously for a few milliseconds, it draws a huge amount of power. Let's say that the fixture might draw 100 watts in normal steady state operation. It might draw 1,000 watts or 5,000 watts for those few milliseconds. So when we imagine now switching on and off an entire theater's worth of hundreds of fixtures, in order to do that, the electrical infrastructure would have to be designed in such a way that it would become impractically expensive. So inrush current, remember that. It's a very important characteristic of LED fixtures that we're going to come back to. That requires sequencing of branch circuits in the theater to turn on lots of LED fixtures. And that leads us back to control by branch circuit, not by the whole system at once. And that, again, leads us to the through power module as an excellent way to gain that branch circuit relay control that can be selected as a dimmer, a non-dim, or with a true air gap relay. The other thing about switching branch circuits as opposed to switching the whole system is utility, just plain practical utility. We like in the theater to turn certain circuits off and leave others on. You know, we like to leave the work light circuit on at night and turn off all the front of house circuits. So the idea of having individual branch circuit control gives us a lot of flexibility and utility, and it's important that we maintain that in this transition to solid state lighting. So let's talk about a new system that we might be installing or specifying and putting in a theater today. How would we do that? What would it look like? Well, one approach might be the situation that we just described, where we actually installed a dimmer rack, a centralized dimming system with through power modules in it to allow that flexibility for the customer. For the end user, not the customer, the end user. But a slightly more progressive approach might be to move to having all circuits in the theater be switched relay circuits. Right now, that would assume, okay, all fixtures are going to be LED fixtures. Well, that isn't going to be the case in all but the lowest level venues. We're not going to design an opera house in the year 2013 that is all LED fixtures. It's just simply not going to happen. So LED fixtures remain in certain higher end of the market as specialty devices that are very useful for some purposes, but still not complete replacements for tungsten. So if we had a theater with all switched circuits in it, we got rid of our centralized dimming system, we're then faced with a problem. How are we going to control tungsten loads that we might need to put into the facility? And we have an answer for that at ETC. The fairly new distributed source 4 dimmer, which is a local dimmer that lives at the fixture and plugs into a constant power relay switched circuit and allows a tungsten load to be connected to it. And of course, an important fact about this product is that it's dead quiet, because when you start taking hundreds of dimmers and moving them from the dimmer room out into the performance space, you have to assure that you're going to have absolute acoustic quiet. And the design of that dimmer allows the very, very low 0 dB at 1 meter, 0 dBA at 1 meter, low noise. a lot of, how many of you guys are electricians or designers? Yeah, I see a couple of you are. Well, you know, there's a force of evil in the theater right now which says, well, as we're moving to solid state lighting, let's change a lot of other stuff, because we can, right? Let's cut down the number of branch circuits in the theater, and let's cut down the number of connectors on the branch circuits, because almost every LED fixture that we see has the capability to daisy chain one fixture to another. So why do we need all these permanently installed outlets? Well, one thing we have to fight to do is preserve the utility and the workability of the systems that we're putting in. We don't, in our move to solid state lighting, we don't want to create take a take-in time of a show that takes 7 hours to put in and make it be 27 hours because we don't have enough outlets in the theater. So this preservation of the number of outlets and places to plug things in is a very important thing, we feel. We don't want to create a daisy chaining nightmare where you have to go from one fixture to the other. We want to be able to hang a fixture, find an outlet to plug it into, and oh, by the way, not do a lot of calculation. Right now, when we plug a tungsten load into a 20 amp circuit, we know intuitively how many can we plug in. We can put 3 or 4 575 watt loads on a 20 amp circuit. It's pretty straightforward. But when we start daisy chaining LED fixtures together on switched circuits, it becomes a little trickier. Because remember, let's go back to my statement about inrush current. All of a sudden, the number of LED fixtures that we can plug into a circuit is not dictated by their steady state current draw. So we can't just add up, oh, I have 20 100 watt fixtures, so I can plug them into a 20 amp circuit. Doesn't work that way. The inrush current of turning these devices on all at once will be tripping the circuit breaker. So we have big derating factors that we have to apply to how many LED fixtures can be plugged into a single 20 amp circuit. That means it's not smart to get too draconian with cutting the number of 20 amp circuits. Because while the steady state power draw won't need lots of 20 amp circuits, the inrush factor will. And depending on the type of fixture we're plugging in and the type of dimmer or relay that we're plugging it into, the derating factor can be large, like maybe half. Derate half the number of, half the amount of steady state current into a 20 amp circuit if we're using capacitive switch mode power supplies in LED fixtures. So the other thing that dictates how many fixtures can go in a circuit is how many tungsten loads do we need to accommodate. If we're working in a high-end facility that's going to have a pretty even mix or a tungsten dominant system for a while, then we need to make sure there are enough 20 amp circuits and enough outlets to service those higher wattage tungsten loads. In any event, from our point of view, we believe the 20 amp circuit still is the weapon of choice in even a new facility. Some people have also suggested, wow, we've got a great idea. Let's change the connector that we've been using for the last 20 years, whether it's a pin connector or a twist lock. Why do we need these big connectors when we have these very small fixtures that don't draw much current? And of course, you don't have to look very far to get a candidate for a new connector, because right on the back of the LED fixture is likely to be a Neutrik Powercon connector. And everyone says, wow, that's so small, it's so nice. Why can't we just put that throughout the theater and get rid of these big pin connectors which aren't needed for these low wattage loads? Well, anybody work in a facility with weird connectors in it? Like non-standard connectors? Well, if you have, you know it's a nightmare. Your world becomes about adapters. because the next show that comes in or the next rental equipment that comes in is going to have the standard connector, but you have the new improved weird connector, right? So this doesn't generally work out very well. And you got to really think about the vast installed body in the world of theater or entertainment, just in the US, the vast installed body of standard connectors, and say, wow, do I really want to change the connector on every outlet in the theater to something that no one else has right now? Might not be the right time to do this. We really have to consider that carefully. The other thing is, just from a straight technical point of view, the Powercon connector can't accommodate the size of cable that the National Electrical Code requires in the theater, extra hard usage cable, type SO. Its cable entry isn't big enough. That's number one. Number two, the Powercon connector is listed as an appliance connector. That means it's designed to go on the back of an appliance like an LED light, not be used as a general purpose connector. So that's an important consideration. We're not ready to adopt the Powercon as a standard connector. So next, let's move away from power distribution and talk about control for a minute. The most profound change that solid state lighting brings to the theater is that every fixture in the theater in an all LED or all solid state rig is now going to need data. Now, we're used to some things in the rig needing data, and we're pretty comfortable with it. A color scroller, some moving lights. A lot of lights require data now, but not every light in the theater. And that is a huge scale issue, to go from some lights to all lights needing data. And that also gets people thinking crazy thoughts. Because how am I going to do this, right? I don't want to be running cables all over the theater, because now I have to run a cable to every light. It's too hard. I know, I'll use wireless. Well, maybe not. We think at ETC that still a wired data infrastructure is the weapon of choice, simply from a reliability point of view. Look, wireless DMX has a lot of advantages for special applications where you can't get a cable. But if you have the ability to run a cable to a light, it's going to work every time. And so that's something we think is important. The other thing is that now we've got a theater full of lights that are all configurable, right? They all have settings, address settings, mode settings, is redshift turned on, what's the curve of the light, all sorts of things that need to be configured on a per fixture basis. And this is where SneakerNet fails us, right? When you get in the theater and you are in a condition where you have to run to every fixture to configure it, it's no longer a very practical situation, right? So how do we solve that problem? Well, we think RDM, remote device management, which is a command and configuration protocol that runs over the DMX wiring network, we think that's going to be the killer application for eliminating all this running around the theater and allowing us to monitor, configure, and control all these intelligent fixtures. It's going to provide a robust data infrastructure and a very powerful configuration tool. ETC systems have this integration. Our fixtures speak RDM, our consoles listen to RDM, and our network gateways pass RDM data. We also think that big DMX networks are not the answer here. We think that Ethernet networks with DMX as the last mile between the network gateway and the fixture or target device is going to be the way to go. So in conclusion, I think we can see that solid-state lighting systems have many gotchas in them, and some of them are hidden, like this issue of inrush current. getting a reliable system installed is not necessarily easy. And we have new system tools from ETC to support a rational transition from tungsten to solid-state lighting. You know, this is a continuing dialogue that we're having with end users in the market, and we welcome your opinions on this. And I'm sure in the fullness of time, we'll arrive at the right system design for solid-state lighting. Thanks for your time.